let's get started. What I would like you to do is I'd like you to summarize all of the reactions that you know. Okay, starting from when we started with doing the formation of haloalkanes from radical halogenation. Okay, now I'm going to summarize what we discussed with alkene reactions right now, and then we'll try an organic synthesis. Okay, so first we started off looking at addition, electrophilic addition. So you're going to have to add an electrophile across my double bond, followed by a nucleophile. So if we do addition of water, use an acid catalyst like sulfuric acid. Why don't we use something like HCl? We discussed that because if you form a chloride in the process, it's not as reversible as if you form an alkyl sulfate. So add in the H plus as my electrophile, then my nucleophile, the water comes in, and I regenerate my H plus. The thing about when you do this reaction, you always get a Markov-Nikov addition. So the hydrogen goes on the least substituted carbon, the hydroxyl goes on the most substituted carbon. But more interestingly, because you're forming raw carbocations, you get a lot of rearrangements adding water this way. Okay? If you don't want rearrangements and you still want Markov-Nikov addition, then you can use mercuric acetate in water for my first step. Okay? Followed by reduction with the sodium borohydride. In that case, you get the Markov-Nikov, but you don't get a rearrangement. Suppose you want an anti-Markov-Nikov addition of water, then you use hydroboration oxidation conditions. You use borane THF for my first step, and you form the four-center transition state, followed by oxidation with hydrogen peroxide and sodium hydroxide. Okay, so you get an anti-Markov-Nikov, and be aware that my hydroxyl group and my hydrogen have a syn addition, so you could get stereochemistry there. Okay. We also talked about the addition of HX. So again, here is my alkene. And you can add HX, where HX is either HCl, HBr, or HI. Okay? And what you can get is basically addition across your double bond. Okay? And again, this is Markov-Nikov addition. Markov-Nikov, and you can get rearrangements. Okay, suppose you wanted to do an anti-Markov-Nikov. We can do the anti-Markov-Nikov only for HBr by the addition of a peroxide. And you're going to need just a little heat on the peroxide. Okay, the reason you need this is you're going to add HBr using radical addition. So you're going to form the radical, okay, and then basically it's the radical that takes off, makes a radical out of this, and then you'll form the most stable radical before you add on the Br. In that case, this is an anti-Markov-Nikov. Okay, and you're doing a radical halogenation. Okay, what happens if you have an alkene and you want to add on the allylic side? Remember, basically, I'm putting this not because it's adding across my alkene, but remember we're going to use NBS. Okay, and that will actually form bromine in very low concentrations and you form HBr as your byproduct, so that regenerates it. Because remember, you have a competition between the addition of bromine onto my alkene versus a halogenation. So just be aware. This is an allylic substitution. Okay, so one of the things that you're now seeing already is that we have to be aware of competing reactions so we can decide how we want to actually do our reaction and what reagents to use to avoid competition. Okay, so that's adding HX, Markovnikov, and adding HBr, anti-Markovnikov. We can go ahead and start taking a look at adding my halogens. If I add my halogens, this is chlorine, bromine, could even be iodine sometimes, okay? And if you look, we don't often write down the solvent, but if you look at the solvent, be aware that our solvent would be something like dichloromethane, okay, but not water, okay? So if you see this, you say, oh, that's my solvent, okay? And what you're going to do is you're going to add your halogen, but it's in the anti-orientation, anti-addition. Okay, and remember you go through the halonium ion. Okay, so how is this different than if I have X2? In particular, we're looking at chlorine or bromine. And instead of having something like dichloromethane or some other solvent, we have water. And now what we've done is we formed a halohydrin. This is Markovnikov orientation, and it's anti-addition. Okay, so now if you say Markovnikov, which is which? In terms of the electrophile and the nucleophile. So your halogen is my electrophile, and my hydroxide is going to act as my nucleophile. Okay? So this will add on from the most stable carbocation, and then you add in the water. So it's X2, H2O. Okay, so just be aware when we say Markovnikov, unlike hydrogen and having a clear electrophile and nucleophile, sometimes people might wonder, what's my electrophile and nucleophile? Halogen's my electrophile, and nucleophile is water. Okay, so that's working with your halogen so far. Okay, so what else did we learn? We learned how to, we did acid catalyze. Let me just make sure, oxymercuration. Oh my goodness. Let me talk about making ethers. We talked about the alcohols. Let's talk about ethers now. So to make ethers, you could actually, just instead of water, and again, it would be the same thing. It would be Markovnikov, and you get rearrangement. Okay? More often what you'll see though is using your mercuric acetate. Instead of water, you have an alcohol for your solvent, and then we reduce using sodium borohydride. and you would get your Markovnikov orientation. Okay, so we have those. And then finally, let's talk about the rest of the reactions. So all the ones that we just discussed have to do with electrophilic addition, where it's clearly you add in your electrophile, general mechanism. Okay, so here's the general mechanism, and then with each reaction, just take a look and determine for your mechanisms the small tweaks, like with the borane hydroboration, you've got the first under transition state. With just adding a halogen, you form the halonium ion. But essentially, the general mechanism for these is you have your electrophile, remember, you're looking for the most stable intermediate. Okay, adding your nucleophile. So your final product is an addition across your double bond. Okay? Alright, so let's go on to our next set of reactions. Okay, so these reactions, we have hydrogenation, okay, and you need a catalyst. Remember, we're talking, it could be palladium, it could be platinum, it could be nickel. Alright, and you just add hydrogens across your double bond. Remember, this is a syn addition. Okay, then we did carbenes. Okay, so when we do your carbenes, the major ones that you want to know are your Simmons-Smith, okay, that's your Simmons-Smith. Now, since it's concerted, you're going to have to be aware. I'm going to put an R group here and an R group here, just so you are aware of its stereochemistry. Okay, so since it's stereoselective, be aware that you may form enantiomers. The other one is alpha elimination. If you do alpha elimination, you have something like either chloroform or bromoform, something like sodium hydroxide. And when you do form your carbene, this is a dichlorocarbene. And again, it's concerted, and you have to worry about stereoselectivity. So those are your two carbene chemistry reactions that you need to know. Okay, so let's move on to our next set of reactions, which is basically epoxides. And basically, one way to do it is you form the halohydrin followed by base. What you would get is an epoxide. Be aware there is some stereoselectivity for this reaction. So, for the mechanism, as you recall, for step one, you form your halonium ion, then your water acts as a nucleophile, attacks it, Okay, we talked about this electrophile, and that's nucleophile. Step 2, where I have my base come in. Okay, so now there's a backside attack on my leaving group is my halogen, and now I can form my epoxide. Okay, so just be aware, because your halohydrins give you an anti-addition followed by the formation of epoxide, which is a backside attack. Just be aware of your stereochemistry on your epoxide. What's another way to make it? You should know the mechanism for this is a concerted mechanism, and that is if I add a peroxy acid. Okay, the most common one, you'll see us write it as CO3H. The most common ones, examples for peroxy acids include MCPBA, metachloroperoxybenzoic acid, or peroxy acetic acid. Okay, and in a concerted fashion again. So just be aware of the stereochemistry. You do form your epoxide. Okay. Then we talked about past epoxides. We talked about diol formation. Okay. And with diol formation, one of the ways you do it is you can have your alkene. And the first step is you form your epoxide. And your second step is to break your epoxide. And it's both acid and base sensitive, but we're going to talk about just the acid breakage of your epoxide. When you do that, your diol adds is the anti-addition for your diol. Okay? If you use potassium permanganate, it has to be cold and dilute, you can have it under neutral or basic conditions. Okay, and what you form is you do form the diol, but instead it's the syn addition. Okay, yields are a little poorer, but potassium permanganate is a lot cheaper than if you use osmium tetroxide, which is an excellent reagent, but it's expensive and it's not so easy to discard the waste. Okay, use osmium tetroxide, and after that, I'm going to follow it by oxidation with hydrogen peroxide. Okay, when you do that, what you get actually it's not the same, it's the same steps. I'll put a comma here. Sorry about that. Is again the diol with syn addition. Okay, so how do you make a diol? If you want anti-addition, you're going to go through epoxide and open it with acid and water. If you want syn addition to make the diol, you're going to use dilute cold potassium permanganate with some base, okay? Or it could be neutral, but oftentimes you'll see it with hydroxide. Or you can use osmium tetroxide with hydrogen peroxide. Okay, and then you'll get the diol added as syn addition. Okay, what happens if you continue to use potassium permanganate on your alkene? You can get bond cleavage. So let's talk about bond cleavage. So I can use, do my alkene, if I use potassium permanganate, but in this case it's warm and concentrated, okay, and you would get bond cleavage. Okay, if you have, as we mentioned earlier, a hydrogen here, and you cleaved it with potassium permanganate, it will not stop at the aldehyde stage. It will continue to oxidize until you get a carboxylic acid. Okay, and if I had a terminal pen, terminal alkene you get your carbonyl compound here, but on this side it goes all the way, it oxidizes all the way, carbon dioxide and water. Okay, what happens if I don't want to go all the way to my carboxylic acids or to carbon dioxide? Then what I use, instead of potassium permanganate, is ozonolysis, and for my second step, dimethyl sulfide. In this case, where I have ketones, both will give you the same answer. Okay. If I have, if I have a hydrogen here, then you form the aldehyde. Okay, and likewise, instead of going all the way, carbon dioxide and water, you'll get formaldehyde. Okay, and stop there. All right. So, what about olefin metathesis? What I want you to know about olefin metathesis is what it is. What about polymerization? I want you to know how to do polymerization, but it's just the formation of cations, and instead of just having a final answer here, it just continues to add and to add and to add. So just be aware of those, okay? So before we stop with this chapter, let's talk about retrosynthesis. Okay, let's get started. Before we move on to our next subject, I'd like to just do a retrosynthesis so that it kind of makes you remember all of the reactions that you've done since radical halogenation of alkanes. So in this case, we're going to make this compound from any alkenes or cycloalkenes with no more than 6 atoms. So when you do this, you can say, well, really, the 2 parts would be, I have 1 part here and 1 part here. So where do I cleave the bond? I can cleave the bond on this side, or I can cleave the bond at this side. And we're making an ether. So when you look at this, you say I have an ether and I have a cyclopropane. So with ethers, how do we make ethers? Well, you can have an alkene, okay, and H plus ROH. You can have an alkene. You can have one mercuric acetate and an alcohol, and then I reduce it. Or you can actually do an SN2. You can have an alkyl halide and a base, an alkoxide, and do an SN2 reaction. So we'll keep these in mind. So these are the ways we know how to make an alcohol right now. Okay? Then you have to think about, how do we make cyclopropanes? Well, cyclopropanes, there's only two ways, and this doesn't have any halogens, so we're not going to be doing alpha elimination. So really, there's only one way, because the two ways, one of them is toxic and explosive, so we're not going to use that way. So the only one we know is using Simmons-Smith and carbene chemistry. So we'll do the Simmons-Smith carbenoid. Basically, if you have an alkene, diiodomethane, right? Or, let's see, we have zinc, we have copper, okay? You can also write it like this because they're complex together, and then you form your cyclopropane, okay? So, we know we have to use this reaction. Okay, so what happens if we save it at the end? Well, if we had this, we save it at the end, then I'd have an alkene right there. So, if we work backwards, what we would have and then we would do our Simmons-Smith. Okay, well, that looks great. Now I have an alkene, but the problem is with this alkene, I have 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12 carbons. So it's too big. So we need to break it up. All right, so how do we make an ether? Well, to make an ether, to have basically this as my alcohol, I'd still have to make it, so I have to figure out how to do that. Or I could have this as my alcohol, and I have to have a double bond here. That makes no sense. So if I had this as my alcohol, makes no sense. This is my alcohol, makes sense if you want to do this reaction. Now, what are the upsides and what are the downsides of that? Well, the upside is we can make the alcohol, I think. The downside is if this is an alcohol, I also have a double bond I could be adding to itself, not just to this reagent. So that doesn't make any sense either. So it makes more sense to do the SN2. So the question is, do I make this bond or do I make this bond? So let's look at SN2, and we'll be going forwards this time. If we do breaking this bond, then I'd have to have this alcohol. You can use a strong base like potassium butoxide, okay, or preferably you just use potassium metal, okay, or sodium metal. Now why is this? Remember how sodium metal reacts with water to form sodium hydroxide and hydrogen gas? Okay. Okay. And hydrogen gas? Okay. So basically it's the same thing. If I use sodium metal plus my alcohols, I'll get 2 sodium alkoxides plus hydrogen gas. Okay, so we can use this as well. Just so you're not going to put that down. All right, now I have a very strong base. Okay, so now let's take a look. Here, I just need a good leading group on this carbon right here. Okay, and if I do that, then I can do my SN2. What's nice is this is an allylic carbon, so we can put a good leading group on an allylic carbon, and that's what we're going to do. Okay, so let's start putting things together. We're going to do route number 2, which means we're doing an SN2, and we're going to be forming this bond. Okay, so that means is I need okay, I'm going to add sodium to that to make the alkoxide, and then I'm going to add my alkene, and a good leading group, say, is a bromine. Okay, so now we have to make 2 different compounds. We need to make this one, and we need to make this one. So let's start with making A first. If you notice, I'm going to redraw A so it looks like this. What's implied is a hydrogen, which means I've added HOH, the water, in the syn addition. Also, notice how the hydroxyl is on the least substituted carbon. This is an anti-Markovnikov addition, okay, and it's a syn addition. Well, the only reaction we know that can do a syn addition that's anti-Markovnikov in making an alcohol is hydroboration, oxidation. And when you do hydroboration, oxidation reaction, it's on an alkene. And that's what it would look like. So 1, 2, 3, 4, 5, 6. It's a 6 carbon cycle alkene. So I can stop here. If I had said something like, oh, I would like you to make it from a cycloalkane, then you would just do basically a halogenation, radical halogenation. It will prefer to go on the tertiary carbon, and then you basically do an elimination. Okay? So we can stop here. This is root to make compound A. Okay, so that part's done. Now, let's make B. So to make B, let's see if this purple still works. We need to put on a bromine. Okay, but when we put on the bromine, look, isn't this in an allylic position? Here. So we need to add a bromine to an allylic carbon. And we don't not want competition in terms of adding to my alkene. So to do that, you need N-bromosuccinimide in order to keep my bromine concentration low. Okay. And if you add NBS to your alkene here, it'll actually do your radical halogenation. Okay, so don't forget to introduce some light. Okay, okay, this will add here, and you don't have a high enough concentration for you to form bromine adding on this side. So this is all you need. So let's summarize then what our reaction will look like. Okay, so from my product, you said we're going to do a Simmons-Smith. Okay, and then for my Simmons-Smith, that would be what we would be working with. And this is formed having this alcohol, adding in my sodium metal, and then adding in my alkene. Okay, so let's go here. This alcohol is formed from a 1-methylcyclopentene if I do my boration, hydroboration, oxidation. Okay, and here is compound B. B is formed from 2,3-dimethyl 2-butene by adding NBS. Presence of light. Okay, and that's how you get that compound. And there you have it. So that's how you analyze the synthesis and how you put together your retrosynthesis when you're done.